This video is going to be for Chapter 21 problems 51, 78, and 91. So all from the February 6th homework assignment. And to start, 51 gives us a circuit, and it looks something like this. We have a 12-volt battery, then a 3.9 ohm resistor, and then we have a 1.2 ohm resistor, and a 9.8 ohm resistor. And then in the other branch we have a 6.7 ohm resistor and another battery. Be careful to the location of the positive and negative terminals. We've got positive, negative, and a 9-volt battery here. And A just wants us to find the current between or through each resistor here. So the key to this one is Kirchhoff's laws, and first we are going to use your junction rule, JR there, and your junction rule, if we choose this point right here to be your junction, I am going to call my first current I1 going to the right here towards or through the 3.9 ohm resistor. I'm going to call I2 coming in the other way to the left through the 6.7 ohm resistor, and I'm going to call I3 the one that's going down through the 1.2 ohm resistor. Now you can technically call the directions whichever way you want, and your answer, if it's negative, just tells you that you initially stated that the current was going in the wrong direction, so that should fix your mistake. And so first with the junction rule, you say that all your currents going into the junction equal all your currents going out of the junction. So what we have is 0 is going to equal I1, because that's going into the junction, plus I2, minus I3, because that is the current that is leaving the junction. Now, you've got to apply the loop rule twice. Loop rule number 1. Loop rule number 1 tells us whenever I make a complete loop, your whole voltage has to be equal to 12 volts in this case, or 9 volts. So remembering your rules, our loop number 1, if I start with the battery and go in a clockwise loop in my left part of the circuit over here, I'm going to get 0 equals, whoops, sorry about that camera there. 0 equals, notice right here you are going from the negative terminal to the positive, so that means with our sign conventions you plug that in as a positive 12. And then next, since I'm going with the current, and I'll shift so you can see the picture, I1 is going to the right and my loop is going to the right, I'm going to subtract 3.9 I1, because that's voltage equals resistance times current. And then next one, I'm still going with the current, but now I'm talking about I3, so I'm going to subtract 1.2 I3. And finally, through this 9.8, I'm still going with the current, and that is going to have a current of I1, because the current's going to split, and then it's going to come back together over here. So I'm going to subtract 9.8 I1. And I'm just going to leave it like that for right now. Now, in your second loop, R2 here, if I go in a clockwise pattern again, for this loop I'm going to get 0 equals, now notice in this case if I'm looping clockwise, I'm starting at my positive terminal and going towards my negative through my battery, so that means I plug it in as a negative 9V. Over here with the 1.2 ohm resistor, I'm going against the current that I have drawn, so that means I'm going to say plus 1.2 I3. And then finally, again, I'm going against this I2 up here, so I'm going to say plus 6.7 I2. Now at this point, that's all the physics and the new physics of it, and it's how to solve this system of 3 equations here. And this is when you are going to use matrices. So the matrix that we are going to call A, you are going to plug in as a 3 by 3, and you will have I1, I2, and I3. You don't have to actually plug those in your calculator. And the first one, or the first line, I'll have represent my junction rule. So I have a coefficient of 1, 1, and negative 1 in front of my I1, I2, and I3. So I get a 1, 1, negative 1. My next one will represent loop rule number 1, and my coefficients for this one are Notice I have a negative 3.9 and a negative 9.8 with I1, so that becomes negative 13.7. I don't have any I2s, so that becomes 0, and my I3 is negative 1.2. And then from loop rule number 2, my coefficient for I1 is 0. There is no I1. I2 is 6.7, and I3 is 1.2. Then your second matrix, B, that you are going to enter in your calculator, is going to have all the rest of the numbers that we have left. So our equation number 1 equaled 0. Number 2, we've got 12 that we would have subtracted over to the other side, so that will become a negative 12. And your third one, a negative 9 brought to the other side, would give us a 9. And then in your calculator, what you can do after you enter these three matrices in order to solve them is do A, or the inverse of A I should say, times B. And what you will get is an answer that looks like this: 0.722, 1.03, and 1.75. And what these values correspond to is the 0.722 is your I1, the 0.103 is your I2, and the 1.75 is your I3. And now what these three mean, let me shift so we have some more paper here, or what question A, I guess, is asking us is what's the current through each. So the current through the 3.9 ohm resistor is going to be the same as the current through the 9.8, and both of those have a value of 0.722 amps. The current through the 1.2 ohm resistor is going to be I2 here, which is, or sorry, I3, 1.75 amps. And last, the current through the 6.7 ohm resistor is going to be I2, which is 1.03 amps. And that's part A. Now in part B, they want us to know, is the potential at point A greater than, less than, or equal to the potential at B? And I would say if you look back at your picture here, notice the way we have our current drawn. This is point A right here, and this is point B. So at point, whoops, sorry about the camera there. Give it a second. All right, so the voltage at A is actually going to be bigger than the voltage at B, since the current is going in the way I have the loop here, kind of downward by the I3 there. And notice, after the current passes A, it's got to go through this additional resistor in which it drops off. It goes through another potential drop. And so that's why your voltage at A should be bigger than your voltage at B. And then at C, you're actually going to go ahead and determine this value. And in order to do that, in C, we want to know what is the potential at A minus the potential at B, the difference between them. And in order to do that, all we have to do is find what is the potential drop across that 1.2 ohm resistor. And so we will take the current, which is 1.2 ohms, and multiply it, or sorry, the resistance, which is 1.2 ohms, and multiply it by the current across that branch, which is 1.75 amps. And we get 2.2 volts. And so that is the difference in voltage between point A and point B. Next problem we have is number 78. And 78 is giving us a circuit that looks like this. So we have an 11 ohm resistor, we have a switch, we have a 45 microfarad capacitor, we have a 9 volt battery, and then over here we have a 5.6 ohm resistor. And so in A, they're asking us to look at, is the current flowing through the battery immediately after the switch is closed greater than, less than, or same as the current after the battery has been, or the switch has been flipped and it's been running for a long time. Now first off, immediately after, and I'll kind of do these in conjunction with part B, which is proving it. So immediately after the switch is closed, the 45 microfarad capacitor is just going to act like a wire, and so all the current is going to flow through just this part of the loop here. The current's going to choose the path of least resistance. If it doesn't have to go through the 5.6, it won't. So if we're doing part B, which is asking to us to actually find the current in each branch, we use Ohm's law and we get V equals I times R. So with a voltage of 9 volts, we're solving for I, and a total resistance, if this is like a short circuit of 11, we get your current is 9/11ths or 0.82 amps. Now, once the circuit has been closed for a while, the capacitor charges up, and in that case, all the current is going to flow through your 5.6 ohm branch over here. And when you add, remember, so now the 11 and the 5.6 are going to be in series. If you follow my pen around the loop here, okay, with the switch closed there, the current will go out here and back to your battery. And remember, when you have resistors in series, you add them up, so their total resistance is actually going to increase. And so when you do V equals I times R this time, we still have a voltage of 9. And our resistance is not going to be 11 anymore, but is going to be 16.6 ohms. And so you can solve for the current to be 0.54 amps. So as you can see, the current is greater after the circuit has been running for a long time than it is immediately after, just by the nature of how it's set up and the fact that these two are in series after this capacitor is charged up for a while. The last one for today then is number 91. And 91 is saying a battery has a certain EMF and an internal resistance. It is connected to a 25 ohm resistor, and we know the current through the battery. And when the battery is connected to a 55 ohm resistor, we know that current as well. So we want to find the EMF and the internal resistance. So for this one, we're going to solve two simultaneous equations and do a little system of equations. So the first one says that the EMF that we are trying to find is going to be, for the first situation they give us, it's going to be the current times the internal resistance, okay, plus the current, which I'm calling I1 for this first situation, times the actual resistors. And so plugging in values, I'm going to get this EMF equals, I'll pull out a 0.65, which is the current, and then I'm going to get times the quantity internal resistance, little r, plus 25. And now I can write a similar equation for my other situation that I have, and that's going to say that the EMF in that situation equals current 2 times the internal resistance plus current 2 times the resistor in that situation. And so substituting numbers in, I will get 0.45, which is the second current, times little r plus 55. And what I'm going to do then is solve those two equations, or I'm just going to kind of set them equal to each other, I guess, since they're both solved for the EMF. And so I will get 0.65 R plus 16.25 equals 0.45 R plus 24.75. And that becomes 0.2 R equals 8.5. It's just the math at this point. And little r is 42.5 ohms, so that is the internal resistance of the battery. And then going back to one or the other of your equations, doesn't matter. You get 0.65 times 42.5 plus 25, and you get the EMF of the battery to be 43.9 volts.